Hello everybody, I'm Florian Dubost, and today I'm going to show a presentation about semi-supervised learning for sparsely-labeled sequential data and application to healthcare video processing. This is work done at Stanford University. The general setting is that you have a sequence of data, for example, a little video clip that has sparse labels. So, for example, if you do event detection, you would just have the beginning of the event, but you won't have access to the end time. So what you can do in that case is that you could sample as positive a little subclip that just follows your sparse start label and have a conservative model using only that as positive for training. Or you could sample more samples further away from that sparse label as positives and use that with a risk-tolerant model for your training. The contribution in this work is a training strategy for semi-supervised learning with sparsely labeled sequential data that leverages what I just explained, a mathematical model for explaining and estimating the evolution of classification performance for increasingly noisier event time estimates, so increasingly further from your start time, and finally, a more application type of contribution, method that detects events from video recording of hospital neonate patients with epilepsy. So here are some examples. MNIST, we created a little sequence of images where a zero progressively leaves the image. You could see this as a little movie clip. So positive is when the zero is in the image, negative when it's not. And here the actual cutoff would be here, but we overestimate the end time and we include that sample as positive in our training sets when it's actually negative. Here is the same type of method where we have a person clapping their hands. Here there is a cutoff and they start jumping. And we overestimate the end time and select those two images as positives, although they are negative. And we'll see how that affects the training performance. So if you think of, varying your risk level and where you estimate your end time, you can model that as a product of two sigmoids. First one that takes into account the positive impact of increasing your training set with more positive, true positive samples, and the other one which accounts for introducing false positives in your training set that are going to deteriorate your performance. If you do those experiments on, for example, CIFAR, you see that you have a bell-shaped curve where the optimal performance is for like middle time of event end estimate and risk level. You have similar results on moving MNIST, and it's a bit different on MHAD, which I'm going to quickly explain now, using this example on hospital videos. So here we compare the model with fully supervised method and with pseudo-label methods. And you see that if you select the right risk level, you can have a performance that's similar to that of the fully supervised method, and actually a bit higher sometimes. The reason is that for some classes, the performance doesn't decrease when you overestimate the end time because it's sampling some classes that were not accounted for in your training set and that don't harm the classification performance. The take-home message is that with this sampling method, you can achieve a performance that's similar to the fully supervised approach. And in case of merging classes, such as the one I just showed structuring, you can approximate that aspect, that impact, as a single sigmoid. Thank you for your attention and see you at the poster.